One of the tougher type of questions in the topic of probability is when there's insufficient information given in the question for us to determine an exact probability. In that case, a question may ask us about the greatest possible value the probability can take, as well as the least possible value. In other words, we want to construct an inequality for this probability. Such a question came out in the A-Level H2 Mathematics 2010 Paper 2 Question 8 Part 5. Similar questions also appeared in 2015 and 2018 in the A-Levels. In this first video of 3, we will look at some ways to tackle such questions where we are required to find an inequality or range of values for probabilities. In this video, we will go through some general theory about probability and discuss a few strategies where we can solve such questions. We'll work on an example together and then tackle the actual 2010 Paper 2 Question 8 Part 5. We'll be discussing both the actual examination question as well as a modified, slightly tougher version of the question. This slightly tougher version actually went on to appear in 2015 and 2018, and that is what videos 2 and 3 will cover. So let us discuss some general theory we can use to construct inequalities for probabilities. The most basic inequality for probabilities is that all probabilities has to be between 0 and 1. This is an axiom of probability, of course. So our aim is usually to improve such an inequality. Can we find a bigger number such that the probability of A have to be at least bigger than? Similarly, can we find a smaller number for the greatest possible value of A? If we can do that, we can narrow down the possible values of the probability. One way to do that is through the use of subsets. For example, the intersection of A and B is a subset of the set A. This can be seen from the Venn diagram where this region is clearly smaller than the region A. So hence, the probability of A intersect B has to be less than or equal to the probability of A. Similarly, the set A is a subset of the union A union B. Hence, probability of A has to be smaller than the probability of A union B. Such subsets gives us a quick way to come up with inequalities. We will look at a few more advanced strategies through an example. So for this example, let's say PA is 0.6 and PB is 0.7, and the question asks us to find the range of probabilities for PA intersect B. So for this first method I'm going to discuss, it will be a quick method but could be potentially tricky to carry out. So the reason why we have a range of probabilities is because we don't know how much A and B overlaps. So this first method we're going to do is we're going to try to visualize how they can potentially overlap with each other. So for the first case, we want A and B to overlap as much as possible. Because the probability that A is smaller than probability of B, this will happen if A is a proper subset of B. In such a case, the probability of A intersect B would then be 0.6. What about the other extreme? For the other extreme, we want A and B to not overlap at all, such that A and B are mutually exclusive. However, for this question, this is actually not possible because PA is 0.6 and PB is 0.7. In that case, if we add up the probabilities, we end up with 1.3, which is impossible. Hence, for them, so they have to overlap, the two sets, but we want them to overlap as little as possible. So that will happen in this case, where they overlap as little as possible if the area outside, the probability outside, is 0. Hence, the probability of A union B has to be 1. We then apply our formula for PA union B, which is PA plus PB minus PA intersect B. Plugging in our values of 0.6 and 0.7 allows us to calculate the probability of A intersect B of 0.3 for this other extreme case. So to sum up, we have the two extreme cases where they overlap as much as possible, and we found that the probability of A intersect B in such a case is 0.6. When they overlap as little as possible, we have the probability being 0.3. Hence our answer, the range of possible values for PA intersect B will then be between 0.3 and 0.6. So this method can be done pretty fast, but potentially quite tricky to carry out if we have more than two sets. Hence, I would like to introduce a second method we can do such a question. So we'll attempt the same example again, that PA is 0.6 and PB is 0.7. And for this second method, which is actually my preferred method because this is more systematic, we will just draw a general Venn diagram. Since we don't know the probability of A intersect B, let us denote it with an unknown x. Next, we are given that PA is 0.6. 0.6 is the area of the entire circle over here. Hence, we can fill up the region over here with 0.6 minus x. Similarly, PB is 0.7, so the region over here has an area of 0.7 minus x. To fill up the entire Venn diagram, don't forget that's the region outside. So to get the region outside, we take 1 minus everything we have. 1 minus 0.6 minus x, minus 0.7 minus x. With a bit of algebra, we will arrive at the answer x minus 0.3. Now that we fill up the entire Venn diagram, we ask ourselves, what is the smallest possible value x can be? Can x be 0? Turns out it cannot be 0 because of this value outside here, over here. If x is 0, x minus 0.3 will be negative, and that does not work. Hence, the least possible value x has to be is 0.3. Now, for the greatest possible value, can x be 1? It can't be 1 as well because of this quantity, 0.6 minus x, as well as 0.7 minus x. So x has to be either 0.6 or 0.7 at the very most. It cannot be 0.7 because if we sub in 0.7 into the quantity 0.6 minus x, we will arrive at another negative value. Hence, the greatest possible value for x is 0.6. This allows us to come up with the answer, which is the same as we found earlier using method 1, that the probability of A intersect B is between 0.3 and 0.6. So this second method can be a bit tedious, but I find it a bit more systematic, where we just slowly try to fill in the entire Venn diagram using algebra and unknowns if we have to. So now let's try to apply what we've learned in the actual past year examination question, the A-Level H2 Math 2010 Paper 2 Question 8 Part 5. In this video, I will only be covering Part 5 because that is the part concerning finding inequalities for probabilities. Parts 1 to 4 are about finding exact values for probabilities. Do attempt Parts 1 to 4 on your own. Feel free to post any questions you may have in the comments below if you want a discussion of those parts. So for this video, we will assume that we have already answered part 4 and we found that the probability of A prime intersect C is 0.15. Now we want to attempt the part 5 of the question. Hence, state an inequality satisfied by P, A prime intersect B intersect C. And this is a 1-mark question for this year. So let's see how we can tackle such a question. So we can use the idea of subsets we have discussed earlier in this video. So notice that it's a hence question. So when we encounter the word hence in our exams, we want to make sure we want to use the earlier parts of the question. We have already found that P A prime intersect C is 0.15. Now we are asked for inequality for P A prime intersect B intersect C. We have an extra intersect B appearing in this question. An extra intersection will make our areas smaller. So if you look at the Venn diagram, this shaded region is A prime intersect B intersect C, and this shaded region is A prime intersect C. The first region, it's a subset of the second set. Hence, we have the fact that the probability of A prime intersect B intersect C is less than or equal to the previous answer, which is 0.15. So this idea of subsets is sufficient to obtain the 1 mark in this question. However, we can easily modify this question to make it significantly tougher. Notice that 0.15, it's actually the greatest possible value this probability can take. What if the question wants the least possible value as well? This is significantly tougher if you want to only rely on the ideas of subset. So to tackle that, we will use the strategy we have just discussed using the Venn diagram and algebras and unknowns. So let's take a look at how we can use them. So in the earlier parts of the question, from part 1 to 4, you should have either the question have given these probabilities to us, or we can calculate these probabilities using the information given. So we will assume that we know the probability of A is 0.7, probability of B is 0.6, PC is 0.5, the probability of A intersect B is 0.38, and PA intersect C is 0.35. And now we proceed to fill in the Venn diagram. I usually prefer to start from the middle, so we will, since we do not know the probability of A intersect B intersect C, we will label it with the unknown x. For the next step, we know the probability of A intersect B is 0.38, so this entire region over here is 0.38. This means that this smaller region over here can be found to be 0.38 minus x. Similarly, the probability of A intersect C is 0.35. So this smaller region over here is 0.35 minus x. Unfortunately, we do not know the probability of B intersect C. So for this region, we are left with another unknown. So we have to introduce a new unknown y. Next, we will use the fact that PA is 0.7. So the entire circle here is 0.7. So taking 0.7 minus 0.38 minus x, and minus 0.35 minus x will get us the value of x minus 0.03. You should verify this value on your own. Similarly, using PB is 0.6, 0.6 minus this, minus x, and minus y will get us 0.22 minus y. And PC is 0.5, so 0.5 minus these three quantities over here will get us 0.15 minus y. Not forgetting the region outside. So now we take 1 minus every single term we see inside the Venn diagram. It will be a bit tedious, but if you work it out, we should obtain the value of y minus 0.07. Do try it out on your own. So now that we have the entire Venn diagram filled up, we can try to approach the question again. So a possible modification of the 2010 question will be if the question asks for the greatest and least possible value of P A prime intersect B intersect C. So not just a simple inequality for 1 mark, but a 4-mark question asking us for both the greatest as well as the least possible value. So let's first identify where A prime intersect B intersect C is. So it happens to be this region shaded over here, which is denoted by y. Of course, y is a probability, so one possible inequality we can come up with is that y is between 0 and 1. But let's analyze and see whether y can be 0. So it turns out it cannot be, because if y is 0, y minus 0.07 will be negative. So at the very least, y has to be 0.07. Next, can y be 1? Turns out that is a no as well, because of these two quantities. If y is 1, these two quantities will be negative. In such a case, y can either be 0.15 or 0.22. It can't be 0.22 because if you plug it inside here, you'll still be negative. So the greatest possible value for y is 0.15. Hence, we have the fact that y has to be greater than 0.07 and at most 0.15. So the greatest value is 0.15 and the least value is 0.07. So if we compare and contrast to the earlier question, the easier version for the TYS asks us about an inequality for 1 mark. By using subsets, we can arrive at the fact that this probability is less than or equal to 0.15. But to obtain the value of 0.07 is quite a bit trickier, so hopefully this method we have introduced in this video can help you tackle such questions. These methods can also be used for the 2015 paper 2 question 9 as well as the 2018 paper 2 question 7, so I do recommend you try them out on your own. I'll be recording and uploading the solution videos for these two questions soon, and I'll post the link on them once they are ready.